Maybe you gotta
through this.
It's an expensive hobby.
I know. Exactly. It's like,
How you doing?
that is pretty cool.
Well, I'll just do a quick introduction to get us started here. So we're very pleased, of course, to be able to host Dr. Ricardo Velarde. He's Associate Professor of Industrial and Systems Engineering at University of Arizona. And in his previous positions, he was a Research Associate in Engineering Systems Division at MIT. His research focuses on systems engineering and metrics, cost estimation, test and evaluation, enterprise transformation, and performance measurement. He got his PhD in Industrial and Systems Engineering from USC, and we're very pleased to be able to host you here today.
Thank you. Great. Appreciate it. Thank you. All right. Good to be back. Yeah. So a little piece of trivia. This is a photo facing north in Tucson. That's Mount Lemmon, and that is the southernmost ski resort in North America. But it's not as fun as the one here. So what I'd like to talk to you about today is one of my research areas, which is cost estimation, but in particular as it pertains to systems engineering. There is a lot of work done in this area, mostly in hardware and software, so those problems are relatively stable. Systems engineering, though, is sort of a new area where a lot of people are kind of throwing their arms up and saying, well, how do we know how many system engineers we need for a particular project? Okay, so I'm going to give you a little bit of background and some context. But first, I wanted to give you the big picture, sort of how I think about my research portfolio. So really, there are four themes here. I think a lot about enterprises, sort of the organization and how it ties to the technology, because if you don't have an efficient organization, the technology that's going to come out of it is going to be very mediocre. I think a lot about research methods, because in systems engineering, there's a lot of influence from software, there's a lot of influence from project management and electrical engineering, but we have to come up with our own ways to solve the kinds of problems that are unique to this particular area. I'm going to talk about one quick example that comes out of that group of methods, which is sabermetrics. For any of you who are baseball fans, it's basically statistics applied to baseball. So I'll talk about a quick example there. Modeling is essentially my main area of emphasis, and so most of the talk is going to be focused on how we quantify complexity in systems and how we can translate that into cost. Okay, so that's going to be the core of the talk, is the modeling part. The decision-making part is inherently tied to modeling, because you do modeling for the purposes of making a decision. The model doesn't make the decision for you, the human still has to make it. So that introduces actually some very interesting problems, which some of them we work on. I'm going to talk a little bit, one quick example about behavior change, a project that I've been working on with the College of Medicine at U of A. And fortunately, I've been able to combine these interests into my interest in sports. So I'm going to give you one example is football. So this project has to do with behavior change. And I'm sure all of you are familiar with the issue of concussions in professional football. They're also very prevalent in wrestling, ice hockey, soccer. For instance, my 8-year-old son's soccer league banned headers. No more headers for children under 12. So part of the issue that we're trying to resolve in college football, because that's who paid for this research, is to increase the amount of concussion reporting amongst football players. So how do you convince a bunch of 18 and 19-year-old testosterone-heavy warriors to report a concussion, right? So one way that the NCAA is doing it now is they show them a video. And they say, watch this video, and hopefully this will educate you about concussions. It doesn't work. So what we're trying to do is take the next leap beyond that, and we created a virtual reality game. So the image that you see there on the right is implemented in Google Cardboard. Google Cardboard is a low-cost virtual reality viewer. It's $8, $9 per viewer, and you actually project the virtual reality image on your smartphone. So we created this app called Brain Gains, which again, we didn't name. We actually asked football players, what would be a cool name for an app? And they said, when we go to the gym, we make gains on our muscles. Same idea, you make gains on your brain. And the idea of the game is to put you through a scenario, in this case is to catch a punt. And when you get hit, you start experiencing symptoms of a concussion, like blurred vision, delayed reaction time, sensitivity to light. And our hypothesis for this project is by experiencing something that's more visual, you're more likely to report the real thing. So phase 1 of the research is to implement the app, test it. You'll notice that the actual stadium is Arizona Stadium. Phase 2 is to actually validate to see whether our hypothesis is true. Do players who experience the virtual reality concussion report a real concussion when they get it? Okay, so that's the issue of behavior change. Again, it's using technology to try to accomplish that goal. Another project that I will just briefly tell you about is a project called the Science of Baseball, which is sort of just grew out of a very rudimentary statistics weekend camp for middle schoolers, and now has sort of grown into a company. We actually started a spin-off company from the University of Arizona where we use various examples in STEM to get kids interested in math and science. So we call it edutainment, right? Kind of hide the education into the entertainment. So the example on the top left is the kids learn how to launch baseballs at different angles of trajectory, and they see how far it goes. And they recognize the connection between angles and horizontal distance of a baseball. On the top right, that's kids learning about reaction time and fielding percentages. Those two pictures are at Salt River Fields, which is the spring training stadium for both the Arizona Diamondbacks and the Rockies. And then on the bottom left was actually some work I did with the Rockies last year, where we brought a group of middle school and high school teachers from surrounding areas, and we taught them all the lessons that we knew, and we put them all in the context of the Colorado Rockies, and now they've taken that information back to their schools to, again, same idea, get kids interested in STEM through baseball. So those are two of the projects that I've been working on, but I'm going to talk about the project that pays the bills, which is the cost modeling project. So this is really the summary of what I do. Create cost model to help people make decisions, okay? Because the idea is a lot of, engineers are trained to optimize the technological part of the system. And they don't really think about the cost necessarily, because the cost is a byproduct. Let upper management, let people in the corner office worry about cost. Well, so that is no longer acceptable in industry, because the way we think is a solution that is too expensive is not a solution, right? So that's what we're teaching, and that's what we should be teaching in all of our engineering courses. No matter how fancy your solution is, if nobody can afford it, you got to start over. So the three takeaways that I want you to remember from the presentation, the first one really is the sort of logical flow between how you get to cost as a function of complexity. So if you can model complexity in the context of systems engineering, and I'll explain to you how I do that in my particular model, then we can come up with some sort of measure of size. And size in this case is functional size, not physical size, but functional size. How many functions, how many things does your system do? And the idea is the more things that your system does, the more effort it takes to design, implement, maintain all of the engineering person months that you need to pull that off. And then that leads you to cost. Okay? So a lot of times, in terms of research, we don't actually make the last step of translation to cost, because that's really a business decision. We often just stop at effort. So if we can reliably tell somebody, these are how many person months of effort your project is going to take, that's 99% of the solution. Translate that into some currency, that's an accounting step. The other takeaway is really one of the conclusions of the model is that requirements understanding is one of the two main cost drivers of system engineering costs. Not a big surprise, I hope. The other are the ilities. Any word that ends in ility, reliability, maintainability, survivability, interoperability. The more of these ilities that you have, the more expensive the system is. So the challenge is quantifying these things and then validating that they actually do make a difference, that they correlate with cost and effort, okay? And then the third part is really just an extension of the work, where a lot of people, especially in large military projects, are trying to figure out how much system engineering should I allocate to my project? And the question is, what's the right amount of system engineering? There's sort of the optimal amount of system engineering. In some cases, the project may be simple. It may be expensive, but it may be simple in terms of its complexity. So you don't need a lot of system engineering. In other cases, the project may be extremely complex. So you need to know what those right parameters are in order to figure out what's the return on investment. If I hire 5 systems engineers, am I going to get what I expect out of it? Okay, so it's an optimality question. Let's skip this and go right into the sort of foundational ideas that drive this research. So you can look at the question of cost estimation from a number of theoretical lenses. The first one is looking at this from a socio-technical perspective. So not just the technology in isolation, not just the people, but how do those things interact? Okay, and quantifying those things into items that can be measured. The advisor that I had for my doctoral program was Barry Baim, and he was the creator of the area called software engineering economics, which was really the first field in the 1970s to quantify why software was complex and how you could turn that into decisions about how many people you needed to hire to implement software. So this came out of TRW, which is now Northrop Grumman in Southern California, and now has sort of a whole cottage industry of people who build software cost models for a living. Okay, so that's sort of the genesis of my work. Herb Simon from CMU, the idea of bounded rationality, that people make very rational decisions sort of within an immediate sphere, and beyond that they're extremely irrational. So using that information and how you build a cost model, what parameters you put into it, is pretty critical, because ultimately it's humans making decisions. Adam Smith, total cost of ownership. Obviously, anybody who's building a system that is responsible for its entire life cycle has to worry about the entire cost, not just development costs. Cybernetics, how systems work together, how they interact, and what are the dynamics that make those things more expensive or less expensive. And then finally, the two Nobel laureates in economics, Kahneman and Tversky, came up with these ideas of people making good decisions, but also people making very bad decisions. And trying to really understand, in cost estimation, the number one impact is optimism. We all are optimistic about everything, about our sports teams, about our ability to finish a project by the deadline, right? And this is chronic in cost estimation. So how do we account for that when we're calibrating a model that uses historical data, right? So I'm going to talk a little bit more about that as we get into it. So speaking of decision making, a lot of the research in cost estimation draws upon the idea of making a prediction about the future and using models as an oracle. And this particular image from the Sistine Chapel in the Vatican is of the oracle at Delphi, which is from Greek mythology, the story about a woman who had some superpowers. If any of you saw the movie 300 about the Spartan kings, there was a character like this. She was inhaling smoke and had these extreme superpowers to be able to tell the future. And so you'll hear the word Delphi a lot used in the context of cost estimating, because it refers to this woman, this oracle of the city of Delphi in Greece. But people now use it in the context of how do you get multiple experts in a room and get them as an aggregate, make them to make a prediction. Because the idea is that multiple inputs are more accurate than a single expert. Okay, this has been proven time and time again. And that idea, that methodology of collecting expert inputs from multiple sources is called the Delphi methodology. Right? So we're going to be talking about that a little bit more. Now, tying this to systems engineering a little bit. So one of the, the main text that I use for the class I teach at the U of A is by Blanchard and Fabrici, two professors from Virginia Tech. And they have a variety of key concepts that they provide, and I think the most relevant one to this discussion is the idea of making decisions throughout the life cycle, the x-axis, making these decisions over time. So this solid line here represents how many decisions you have to make in terms of the technology, the platform, the architecture, the cost, the personnel. And so the slope of that curve positive and is very, very large at the beginning, basically saying that all the important decisions are made at the beginning, right? But also at the beginning, you have the least amount of information, right? So think of this line, this dotted line here, labeled system-specific knowledge. So you know very little, or you don't know a whole lot about how the system is going to be used, who's going to use it, how long it needs to last, yet you need to make an accurate cost prediction, right? So that's the rub. The rub is the delta between these two lines. You have to make a whole lot of decisions, yet you know very little about it. Eventually, that problem goes away, but it may be too late, right? So the idea that we're trying to come up with, or the problem we're trying to solve with cost models, is we're trying to move this line up so that there's less of a gap at any given point in time. And at this phase, in the conceptual phase, is where you're making all your commitments. That's when if you're Boeing or Lockheed or Raytheon, you're going to Congress or to the Pentagon and saying, we need $800 million for this piece of software. And the Pentagon's going to ask, how'd you get to 800 million, right? Plus or minus a couple of million? You know, that's a huge delta, right? The one thing that I disagree with this diagram, by the way, that I've already sent the authors multiple emails and they've never changed it. They say, first of all, this is a notional diagram, so that's kind of their scapegoat. This line here about what you're committing, I don't think starts at 0. Because I think it starts somewhere above 0 because some decisions have been made for you. You go into an environment and you have to make an upgrade to a platform, or you're modifying an existing system. Well, guess what? You can't choose a new operating system. It's already done, right? So maybe that resolves some issue about how much you know about the system, but it definitely doesn't start at 0 in a lot of these cases. But the last line that I'll point out is ease of change, right? Making any changes to the system become exponentially more difficult as you move on. And you can think of the inverse as the cost of change. So sure, we can add an interface there, or we can remove a component here. Everything is fair game at the beginning. But once we start manufacturing things, bending metal, we start shipping product, it's going to be extremely complex and difficult to make these changes, okay? So by the way, that's where companies make a lot of money, right? We'll talk about that one a little later. So I'm sure you have seen this diagram or a diagram like that we call the iron triangle or project management triangle. And a lot of people like to think of it as sort of these three things having to be in balance all the time, right? And again, as engineers, we just really care about delivering, meeting the requirements, delivering, making sure that our project or our technology is better than somebody else's. And the cost is essentially a byproduct. So the way I teach this in my cost estimation class is you start at the top. Tell me what the system needs to do in terms of performance, capabilities, functions. And from that information, I'll use a cost model to answer the cost question. Okay? And guess what? The cost models also help us answer the duration question, how long it's going to take us. We're not guessing on this information. We're actually using historical data to make those inferences. So the flow is clockwise. Tell me what the system has to do. I'll tell you how much it should cost. I'm not sure it will cost that much. It should cost that much. That's an important nuance. And then this is how long it should take. I don't know how long it will take. That's a probability. I'll tell you how long it should take, right? So the problem with unrealistic expectations is a lot of times folks cut the cost, but they don't adjust the scope, right? And that's when you start getting into trouble. So the cost models actually, they can accept that modification, just a reduction in the cost, but no modification in the performance. But what the cost model does is it penalizes you. It reduces your probability of success. In other words, if your cost estimate said, I am 80% confident that this project will come in at this cost, okay? But if you change only one parameter and don't adjust the scope, that probability goes from 80% to 60 to 40 to some number very close to 0 eventually, right? So that's one way that we can address that uncertainty in the model. let me show you a little bit more background information about systems engineering at NASA. So this is not my work. This is work that was done a couple of decades ago, but it keeps coming back to haunt me. So I've seen this particular chart presented at system engineering conferences, cost modeling conferences, and people always arrive at the following conclusion, which I think is extremely frustrating because I think it's incorrect. On the x-axis is the percentage of the engineering effort that's allocated to systems engineering. Again, so there's mechanical engineering, there's software engineering, there's project management. So there's a bucket that's reserved for systems engineers. Okay, and I'm going to define what system engineering is in just a moment, but just bear with me. So this is a percentage of the total technical effort that's allocated to systems. Y-axis is a cost performance ratio. Essentially, if you're at 1.0, it means that you came in on budget. If you're at anything above 1.0, it means you overran. You were more expensive than you planned. Okay? The first thing you should notice is most NASA programs overrun. No surprise there. Your tax dollars at work, right? So this is the conclusion that people come up with when they present this chart. They say, well, obviously, the optimal amount, and they use that word, optimal amount of system engineering is 15%. That's what they present at conferences. And I've sort of gotten tired of being the guy who points out the fact that there's actually no correlation there, right? Sorry to tell you. Because guess what? Some projects didn't spend very much on systems engineering, and they were successful as far as this definition is concerned, from a cost performance standpoint. Other projects spent a lot less, and they blew their budget, but there's no correlation here. So this is my departure point. I want to ask the following question. By the way, each dot up here is a NASA satellite or exploration program, or so there are billions of dollars for each of those data points. So the question I want to know from those NASA projects is, well, can you tell me how complex they were? Because I think that would be a better predictor of cost. And I'd be able to tell in a much more reliable way how much system engineering each one of them should have gotten. And yes, these other ones were successful from a cost standpoint. They spent a lot of money on systems engineering. And my argument is maybe they spent too much. So it's, again, a trade-off here that we have to examine. Okay, so I used system engineering as a term multiple times. This is the definition that we use for purposes of cost modeling. So rather than reinventing the wheel and coming up with our own definition, we said, hey, let's use an industry standard, EIA 632. So step one is defining what are the tasks that systems engineers do. And there are similar standards for software engineers and mechanical engineers, but what we then went off and did is collected effort data. How many person months did systems engineers spend doing each of these activities? And as you can imagine, each project was different, right? And it depends on whether you're building missiles or you're building airplanes or aircraft carriers. The distribution of effort was different. It's fine. We'll accept that, okay? We can work those differences into the model. But the idea is that regardless of whether you're building things that float or fly or go up in space, those activities are going to be done at some point. In different proportions, but they're going to be done, right? And one of the differences is if you are building a new technology, it truly is R&D. And from a technology readiness level, it's relatively low, right? So you are literally trying to prove that the technology works. This is going to require a lot more engineering effort than if you are just modifying an existing product. And you're maybe adding some sensors or extending its capacity. That's a much different story. So the proportions change according to how mature the technology is. So what I've been doing for the past 10 or 15 years is collecting data. And these are the companies that I've been collecting data from. And you'll notice a couple of things. First of all, they're all US companies. Second of all, they're all aerospace and defense. Okay? So in a sense, that's a good thing because they're relatively similar in terms of the products they're building. They all hire the same engineers from each other. They're still stealing people from each other all the time. But the thing that you'll notice in the second column is that they make different kinds of products. Okay, so you've all heard and know of Boeing. You know they make airplanes. Okay, but that's different. Their military airplanes are somewhat similar to what Lockheed Martin makes. Okay, in Marietta, Georgia, but that's very different than the ships that are made in Pittsfield, Massachusetts. And it's very different than the communication systems that are made in Texas, right? So the idea is not just to characterize things in terms of complexity, but it's also to characterize them in terms of how much of these activities are being done on these programs, okay? And again, I'm just talking about the system engineering slice of that pie, right? Because each of these products is very, very different, not just in terms of how much money is being spent on them, but how much new technology is being inserted, okay? So one of these data points, let's take SAIC for example. If I go to SAIC and I say, look, I am trying to calibrate this model, this cost model. I need as much data as you can provide. And they're going to first have me sign a non-disclosure agreement and give away my children, in case any, sign off all that, okay? I'm not going to share the data, and that data will never be published. Right? What is published is the model that came out of that data. So that's an important distinction. So all of the data is proprietary, but the calibration, the adjustment of the model that was influenced by that data is what is published. Okay? So one data point from SAIC looks like this. How many person months of system engineering did I spend on this project? And then all the technical characteristics of that project. That's one data point. It's got about 20, 25 fields, okay? So that's expensive, but this is the only way to really tell, to confirm whether the parameters that we've defined in the model are actually valid from a statistical standpoint, okay? So I'm going to talk about the COSISMO model, which is there on the top, the constructive system engineering cost model. Let me actually define a little more about what the model does in terms of scope. So like any cost model, you have to define what it includes and what it excludes. So one way to characterize tasks over time is, well, what part of the life cycle is included? And our ability to collect data was relatively focused on you build the product and then you deliver it to the client up until that point. Now, the cost model does not include system engineering effort in those latter phases of operations, maintenance, and disposal. And I'll tell you a dirty little secret, that's the 70 or 80% of the life cycle cost is in those items that I excluded. But part of the reason is most of the system engineering effort that is spent in these phases, or the way that it's budgeted, is done as level of effort. In other words, they assign a full-time equivalent person for an X number of years. So there's really no science to it. You just put a person there, and you say, this is your full-time systems engineer for the next 5 years, or for the next 10 years, right? It's the cost of these activities that are more complicated to figure out because they depend on a lot of things. And I'll show you what those questions are that we ask. But essentially, what we eventually can do is allocate cost of at each of these 4 phases. Because depending on military products, for instance, this phase could take a couple of years. This phase could take a decade, depending on the product, right? And so we're talking about months, years, millions of dollars for each of those phases. So eventually we decompose the output of the model into those 4 bins. And the system engineering activities that I showed you earlier, those are the ones that are distributed across these 4 phases. So it's important for people who do cost estimating to be able to know, where does the model end, where does it begin, where does it end, and how does it match up to other cost models that I'm using to be able to deliver a complete bid to the government. And it's a little bit of a game, right? I mean, you would think that in all circumstances, the way to win a military contract is to be the lowest bidder, right? Well, it's no longer that way. the government now uses the criteria of best value. And that's another presentation altogether, because value is subjective, but they are not just looking at cost. They're looking at what am I getting for that cost, okay? And the way that evaluation is made is actually, they try to make it as objective as possible, but there's a lot of subjectivity, because meeting requirements and their ability to deliver things on time is mostly predicted by your ability, what you've done in the past. Okay, so past performance is actually an important component here. So the cost model that I built, COSISMO, is used as follows. You provide first 4 inputs as size for systems engineering. You answer how many requirements are there in the product, how many interfaces, how many algorithms, and how many operational scenarios, right? So again, you're answering these questions at the beginning of the life cycle. So some of these things may not be defined. But what you can do is you can estimate by analogy. You can look at similar products and say, well, you know, a similar missile that I built 2 years ago had 100 requirements. And it looks like the one I'm building now is about the same complexity. So you can use that as a gauge. So you enter that information, and then you answer a variety of questions, 14 questions about the project itself. And I'm going to go into those details in a little bit, but the kinds of questions that are relevant is, what kind of technology are you using and how mature is it? Because you can imagine that an immature technology would be very expensive in terms of engineering person months, but on the contrary, very mature and proven technology is going to be inexpensive, relatively speaking, right? So you answer all these questions, you feed it into the, in this case, a green box, but you can think of it as a black box, and I'll show you what's inside the black box in a minute. And the output that you get is a person month estimate. It comes with a probability because it knows that there is a certain confidence level in each of these inputs. And it uses that information to say, okay, that estimate that we're providing, it's either 90% confident or 80% confident. And it all depends on how confident you were on the inputs. Now, the relationships, the cost estimating relationship that sits inside of here is not proprietary. In a lot of commercial cost models, what's inside of that box is the secret sauce that they want to protect. I don't do this for commercial reasons. I do it for academic reasons because we want to make the best model possible. So we publish.